Hi, let's continue talking about EDTA, specifically talking about conditional formation constants. As a do now to get your brains running again, just to take a look at this without doing any math, given the information, what should be the predominant form of EDTA at a pH of 7? If you need a minute or two to think about this, you can go ahead and pause the video. Otherwise, well, I can talk. Keeping in mind that at pHs lower than pK1, that's the H6Y2 plus. In between the two of these is where we find H5Y plus, H4Y, in between pK2 and pK3. And if you keep continuing, this would be H3Y minus, H2Y, 2 minus, HY, 3 minus, and Y, 4 minus. If we're at a pH of 7, we should be expecting we're in between pK5 and pK6. We have one proton left. So my guess would be that would be the HY3 minus form of EDTA would be predominant. We could go back to those graphs. Do I have one of those graphs really quick to see? Yeah, and we're at a pH of 7. And yeah, HY3 minus is the most predominant. I'll have to erase that in a second. But some information, some thoughts I have about EDTA so far. I think I scratched the surface of this in the last lesson. But EDTA being a weak acid, pretty important chemical property. But then separately, it binds metals. Those are like two different things that it does. The interesting thing, though, is that only the fully deprotonated form, as shown in this image, will bind. There are 6 binding sites, the 4 acetates and the 2 nitrogens, but they can only bind in a Lewis base sense if they don't have a proton attached to them, giving them that lone pair, giving them that high electron density. But that's a big problem, because that fully deprotonated form is only one of 7 different forms of EDTA. Plug in my phone. Is only one of 7 different forms of EDTA. So does that mean that it's 1/7 as effective? There's like this missing piece here where we're only worried about one form. It's kind of hard to then turn around and do all the math that we are used to doing. Even more so. So let's get aside from that. Different thought. EDTA can bind metals. I feel like we can use that information to measure the amount of metal in a sample. Yeah, in food and preservatives, when you're using EDTA, the goal is just to trap all of the metal ions for whatever purpose. But you, just like we've been learning all year, there's the all approach, and then there's the smart approach, where you can maybe use the right amount, or within reason, plus or minus 10%. I feel like if you're going to bind up calcium ions, you probably need some sort of indicator, but that indicator isn't a pH indicator, because I don't think pH factors into this, other than saying the pH has to be dialed right to allow there to be that one of the 7 forms. So I think today we're gonna start on this, but we're not gonna finish talking about these thoughts for probably 2, maybe 3 lessons. But for today, I want to take a look at how we can calculate the amount of metal ion in an EDTA-bound metal solution at a particular pH. That is to say, most in your sample, if you have a sample where you've added enough EDTA to trap your metal, most of the metal will stay trapped, but this is all equilibrium based. So what we're going to do is we're going to take some time to target figuring out at that equilibrium how much free metal is there, how much free EDTA is there. To get into that, we have to talk about these formation constants that that we've kind of talked about in other units, and we've kind of talked about in this unit. In general, like I said, the only active form is the Y4 minus form, and we're going to say that our metal is metal M with charge N. So that should mean that in our reaction, metal M with charge N has the ability to react with Y4 minus, and it will react to make, well, what you're seeing here, but we're going to call this My N minus 4, because that would be the charge of the complex. And just like we saw with other complex ions, we're going to write this in formation notation, the idea of two separate things coming together to make one complex. So but that's really important, because if we're not careful, and if we wrote the reverse reaction, that's not going to give us this standard notation for the formation constant. And then if you go look up reference values, you get the reciprocal of what you want, and it's just a big mess. But we're going to say that obviously this would be our equilibrium expression, where these would be unbound and these would be bound. So basically, instead of products of reactants, we can think of it as bound over unbound. And so the goal today is we're going to target that substance. But this is known as our formation constant. So like I said, not only is EDTA only the active form in this expression, not only is it one of 7 forms, we've got a bigger problem too. The highlighted one is our target, and it's the fraction that is in that form below a pH of 7 is too low to show up on this graph. And there it's already at a, like, I don't know, 100th, 1,000th, I can't really estimate how low that is. So the bigger issue is, let me see, so if we were to try and like write out a mass balance for this, we could say that the formal concentration of EDTA is equal to, your sum of all 7 species. But in our expression on the previous problem, we're only looking at 1. This means that, I guess, if you were to try and do any sort of math, you've got this massive systematic treatment problem using all 7 of 6 of the K values, the mass balance, I don't know, the charge balance. This thing sounds like a massive headache, and you kind of have to recalculate it every single time, right? So if we're talking about establishing an equilibrium, and this equilibrium gets stressed, and this amount of Y4 minus changes in any way, that's going to double back and change everything here, which is really not so much a tiny problem as it is a humongous problem. So the thing I want to point out here is that, until you hit about a pH of 10, I mean, even at a pH of 10, the Y4 minus is only 30% of your solution. This means that if all else was equal, if you had a pH of 10 and 11 and 6 and 2, the higher the pH, the more effective EDTA is, because the fraction that is in the fully deprotonated form is high. If you are in more acidic pHs, as we saw in our graph, these other forms of EDTA dominate, and they are, some people say they're less good at binding metals, like they're worse at binding metals. I think they're almost ineffective at binding metals, because that whole effectiveness is based on that entropy-driven process of using one ligand to bind 6 different sites of the substrate. And if you don't have 6 bindings available, and you're only binding 5 or 4 or 3, you're going to need multiple particles anyway, so that's massively going to drive down our effectiveness. It's just not going to do its job the way it should. That means that based on, we should be able instead, my point is, if we're only worried about the Y4 minus concentration, but we have that mass balance to worry about, we should probably be able to put this together in such a way that we are able to respell things. So this is what I want to do now. I would love to respell this. So going back to what we said, we had this mass balance here where the total EDTA concentration, we're going to use this EDTA notation to equal the formal concentration of EDTA. If we wanted to rewrite this using this alpha, I would say that the alpha for the Y4 minus form is equal to the Y4 minus concentration at whatever situation divided by, well, the total, right? That's kind of what a respelling of this would be. We say alpha is equal to part over whole. And so here the part is Y4 minus, and then we would write all the species, but why not just say EDTA? So we're going to use this, like I said, we're going to use this to say the sum of all EDTAs. You might not get what I'm going for with this, but it's actually pretty neat once we actually get to where we're going. I'm going to rewrite this. So another way to say this is that, nope, that's not what I want. Another way to say this is that at any given time, if you take the total EDTA and you multiply by the fraction that's in the Y4 minus, you would get the Y4 minus concentration. If you had a 1 molar solution at a pH of 10, a 1 molar EDTA solution, a 1 formal, right, you'd know that it's 0.3 molar Y4 minus, because if you solve all of those alpha equations with all those Ks, that's what you get. In another way of speaking, that is to say that for a 1 molar solution at a pH of 10, your EDTA is only 30% effective. Which that there is the actual value of this, because what we can do is we can kind of fold that into our formation constant. So given that we had said this was our formation equation with our formation constant, what I want to say is, instead of going to always figure out what the Y4 minus concentration is at every step of the way and ignoring all of the other forms of EDTA, why don't we embrace it? Why don't we instead say this is always a fraction of EDTA? And we have a mathematical expression for that. We said that the Y4 minus at any time is equal to alpha Y4 minus times the total EDTA, which means that we can actually write that in there. But if we fix the pH, if we have the pH buffered at a certain value, this becomes a constant. This is a constant. There's no reason that we should have two constants on two sides of an equal sign. So what we're going to do is we're going to multiply this over. And what we're going to say is we're going to call it K prime F. And that's going to be equal to alpha Y4 minus times Kf, which is equal to the bound divided by the free metal times the sum of all EDTA. This really pushes the boundaries of a balanced chemical equation, because this conditional formation constant kind of refers to a reaction where the reactants show the sum of all EDTAs and the products show one of the forms. But the way we get around that is that this is a derived constant, using what I said before, where there's always this like hidden thing that says when I say EDTA, I'm referring to all of them, and then when I talk about the bound, I'm only referring to some of them. So if we're at like a pH of 10, that 30% is always tied in. So that it's always just like kind of assumed that we're all on the same page with that. And yes, we're just figuring out the numbers and it would work there anyway. So just to clean things up, there you go. This chemical equation is valid, this formation constant is valid, but then this would refer to something that is not necessarily chemically sensical. But like I said, we're referring to this as a conditional formation constant because it is conditional or effective to a specific buffered pH. Table 11-2, which is basically the only other table I think you need for this entire chapter, the way we're going to go through it. These are the formation constants for your metal EDTA complexes, and this is where it matters that you wrote your equation correctly with the complex on the numerator and the free substances in the denominator. First thing I notice, these numbers are all positive, and that's not new, except for the part where the table does show the log of the formation constant, which is new. So that means for lithium, the Kf for lithium is equal to 10 to the positive 2.95, not negative, which means all of these numbers, that's like one of the smaller ones, obviously potassium's a little lower, these numbers are obscenely large. The binding constants are all absolutely gargantuan. This means that the binding is, yes, going to be 100% like, well, not 100%, but nearly 100% product favored. So at any solution of bound metal, the amount of free metal is going to be hopefully pretty low. So, how do we use this? I mean, oh wait, no, there was one other point I was going to make. It's a little thing. The more you look at this, you can actually start to, if you had like ion sizes too, you could actually start to learn something about the size of EDTA as a molecule and how well it binds to certain things, and that's something really neat to pick out. All right, like you can look at some of these and say it's really good at binding cobalt and it's really bad at binding potassium. So look at cobalt as an ion, look at potassium as an ion. You can actually start to figure out. I think potassium is a very large ion, and that's why it binds less well. And you can also see that between lithium, sodium, and potassium. There's all sorts of fun things that we can see. I'm not going to get into that right now. Instead, I'm going to look at a little bit more utilitarian view of this. So, to take a look at this, we're going to say we want to calculate the free calcium ion in a solution of 0.1 molar bound calcium at a pH of 10. So that is to say, this is our initial. And I need to see something. Yeah, okay. So I have to solve everything here. So the way this will work is we have an initial concentration of 0.1 molar, and then equilibrium is going to take over. Now, like I said, here's our formation constant. Kf for calcium is 10 to the positive 10.65. This is massively large. However, it is not infinitely large, which means that as we establish equilibrium, there's going to be a slight shift back towards the reactants. So let's just write an ice table. I mean, we might as well, right? Actually, I'm going to delete this and move it. I wish I could move my handwriting. Move that. So this should be Kf is equal to 10 to the 10.65. We're going to write an ice table right here. We're going to fit it in. So the initial amount of calcium and free EDTA are both 0. And we're going to say the initial amount of bound is 10. We're going to shift to the left. I have a better way to refer to what I was saying before. So I'm realizing, like, in the back of my head, I'm like calling myself a liar. What I had said before is that this reaction doesn't actually show a balanced chemical reaction, and it doesn't. if you are considering all the acid-base chemistry that goes on. If instead you just talk about, you know, what the EDTA does as a whole, if you call the EDTA functioning as a unit, the idea is that in the bound state, it is all in the Y4 minus form, but as soon as it becomes unbound, more chemistry takes place. Now, if you have a buffered solution, that's not going to affect the rest of the solution very much, but you just have to keep in mind that hidden in this EDTA is some manner of equilibria to be forming like HY3 minus and, you know, and H6Y2 plus, like all of those equilibria are happening. So it's not balanced in that the hydrogens aren't balanced, but this is balanced in that the EDTAs as a whole are balanced. That is to say, at equilibrium, what I've said here is true. At equilibrium, free concentration of calcium equals free sum, or sum of free, I should say. So I know I'm garbling these words a little bit. What I'm trying to say is that once that EDTA is free, regardless of what form it is, the sum of all of those forms is still going to be equal to the sum of the free calcium, which is just staying as calcium. So in a way, this is like, it might look like we're doing hand waving, or conversely, it might look like I'm being overly detail oriented, but I'm just trying to really grasp the concept behind this so it doesn't look like I'm just throwing math at you. That said, let me throw some math at you because our general form here now is, since this is EDTA and this is Y4 minus, we're using the K prime F. That's going to be equal to, now we're plugging in the equilibrium values, it's 0.1 minus x over x squared. And that's going to be equal to alpha Y4 minus times Kf, which in this case, since we're at a pH of 10, is equal to 0.30 times 10 to the 10.65. And so let me write that down over here. So that means that our K prime F is going to be 1.34 times 10 to the 10th, and that's equal to 0.1 minus x over x squared. At this point, I would throw this at a calculator. I'm not gonna lie, these problems throw some pretty nasty solutions in terms of if you put everything in one equation. I would prefer doing the thing where you set two equations and see where they intersect. But when you do that, don't forget that you're setting one of, like, y1 equal to 13 billion. So that's not going to really show up on your graph. However you want to solve it, you solve it the best you can, but x being equal to the free calcium ion concentration is equal to 2.7 times 10 to the negative 6 molar when you solve it correctly. So again, this backs up everything we said before. This substance has such a high binding constant that when you start with a fully bound solution and let equilibrium reestablish, it does so, but you're still massively, massively product favored. I realized that the way I wrote this, you started with the product and bumped back towards reactants. That's because of the nature of how the formation constants are written. As one more practice, I want to go through and see what happens when you dial back the pH. So again, Kf is equal to 10 to the 10.65. Alpha at a pH of 6 is 1.8 times 10 to the negative 5th, which is also really close to the Ka of acetic acid and the Kb of ammonia. Why does this number keep showing up? Anyway, it's the same derivation for this solution because it's the same concentration, it's the same substance. So I'm just going to kind of jump to this. Multiplying them together, we get 8.0 times 10 to the 5th, and that's equal to 0.1 minus x over x squared. X equals free calcium, and when you go through and solve that, you should get 3.5 times 10 to the negative fourth molar. So this is at a pH of 6. At a pH of 10, I have a point I need to make with this because we now have something to make a comparison. K prime F was equal to 1.34 times 10 to the negative, or 10 to the positive 10th, and calcium was equal to 2.7 times 10 to the negative 6th molar. So what do we see? And hopefully this should back up what we already saw. At low pH, calcium 2 plus free is larger. We'd said before, based on our graph, that if only the Y4 minus form of EDTA does any binding, at low pHs there's less Y4 minus. So I would assume that in this equation, the lower the pH is, what ends up happening is those EDTA forms, the Y4 minus gets free and it immediately becomes something else, and this decreases the amount of Y4 minus. That would decrease the ability of Y4 minus and free calcium ion to rebind and contribute back to that equilibrium. So in a way, by lowering the pH, we're removing Y4 minuses. This would create more free EDTA and more free calcium ion, which backs up what we see here. So at low pHs, K prime F is smaller than at high pHs for the same metal. And for similar solutions, the lower the pH, the more free ion there is and the less bound ion there is. In other words, if you want EDTA to work well, you need to dial your pH to at least 10, if not higher. So just to finally sum things up, EDTA binds as Y4 minus only. Y4 minus is in several equilibria. So for a solution of bound metal, the general form is K prime F equals alpha Y4 minus times Kf, which is equal to My over M times EDTA. And our general form for that is going to be equal to F minus X over X squared, which is very similar to stuff we've seen before, but just a little bit removed, which is what I really like about this unit. This is a way that we're now applying things to a new situation, and it's not quite the same set of formulas, but it's close enough that it's accessible. Thanks for watching.